adjusted to this. So that's my poor excuse. So let's get started. So today we have 2 lectures back to back, and we will talk about protocols, layers, services, and look at a few examples to sort of set the general scene for things. And then tomorrow, Friday, we also have a lecture, which will then start at the bottom, at the physical layer, and then we will talk about physical layers for a couple of lectures, and then again move up in the stack. So, but let's start with before we start, actually, some announcements. So if you, project groups will be...
They are already assigned.
Okay, there we go. They're already assigned. So if you're here and you haven't been assigned to a group, that's a problem. And that is typically because we don't know that you exist. And then you should send Shoaib an email, and then we'll squeeze you into a group somewhere. We'll fix it somehow. Okay, and then there is a kickoff meeting for the project groups next week. All right, so let's talk about networks. So what are networks? They consist of many pieces, right? So in essence, we have this cloud abstraction for a network, and then we have some applications which is running on a host computer which is attached to this network, needs to talk to some other application at some other node. So inside this network there is a bunch of different things, but we can sort of distinguish them with some basic names here. The boxes here are called nodes, and in between the nodes there are links. Okay, so that's the very basic classification of stuff. The host computers here are those who are running user applications. The hosts are on the edge of the network. Okay. While the routers here are typically not running any user application. So a web server or a web browser or anything like this is not running here. It's running on the host computers. Okay. Okay. So at the very basic level, we have application software, which is running on a host. The hosts are attached to the networks, and inside the networks there are routers and there are links. Okay. Questions? No. Okay. So the problem with this field, I would say, is that there are many names and many definitions of these names floating around. So whenever you read a secondary source or you Google something like this, you will get maybe slightly different terminology. Okay, so that's an unfortunate fact of this field. But I will try to be consistent with the terminology used in this class, and sometimes mention, okay, so sometimes this is also called this and that, right? But anyway, so when I talk about an application in this course, what do I mean by that? Well, it's something that uses the network, a piece of software that's a user software which uses the network. So for instance, Spotify, Skype, or like Amazon, or something like whatever you would use on your terminal, your laptop or your phone, is what I call an application. Sometimes called an app or a user. Okay, a host is something that runs software to support the applications. Okay, so that's software which is run here. The laptop here, for instance, if I do web browsing, is a host, right? And sometimes these are called also end systems or end nodes, source, sink, source for generating data, sync for consuming data. It's also called edge device. Okay, so the definition is that it runs software to support these applications. And it could be a cell phone, laptop, or a server. Something which is attached to the network. Now, router is something that relays messages between incoming and outgoing links. So if you remember on the previous slide here, the router here just basically moves data from one link over to another link. That's the purpose of the router. There are other names here also: switch, hub, node, or intermediate system, and they have there are variations of the same basic concept, is to move data from one link to another link. And we will talk a little bit more about switches and hubs in general as we go along in the course. But for now, let's just think of routers as something which is inside the network and moves data from one link to another link. So for examples of this would be a Wi-Fi access point, for instance, or an ADSL modem. Now, a link, sometimes also called a channel, is something which connects these nodes. Okay, so the cable, fibers, radio channels, and so forth. Okay, so these are some basic definitions. Okay, so let's talk about these networks here. I mean, they are, if we look at internet, the internet as we know it, the internet with a big I, that is probably, one can make a case at least, that is the biggest machine on earth, right? And it's a super complicated machine. Nobody knows how big it is. We don't know, right? And it's super complicated with all these interacting devices of various sorts, running different operating systems, and so forth, right? So, and somehow it works, right? So it's a very complex thing, but there's a lot of interacting pieces, both routers, switches, cables, radio channels, and protocols, right? So both hardware and software which is interacting in a very complicated way. So when designing a very complex machine, whatever it is, how do we deal with this? Well, typically if you have 100 engineers, you try to engineer something, they cannot work on one monolithic design, right? You typically divide up the machine in smaller pieces. You put the design team on each of these pieces, and they design that piece, and then everything is glued together to form the complete machine. So the classical approach then to dealing with all complex problems, I would say, is divide the problem into smaller pieces, more manageable pieces, and then you design each piece, right? So split the overall problem into sub-problems, solve each sub-problem, and then glue the sub-problem solutions to a complete solution. Okay? So in principle, this sounds very simple, right? The difficulty with this approach is that one has to have very precise interfaces between the pieces. I mean, if you're building a puzzle out of pieces, they better fit together, otherwise you would never complete the puzzle. So step 3 here is in the gluing of the sub-problems into a complete solution requires very well-defined interfaces. But assuming that we have this, we can essentially tackle very complex problems in a manageable way. Then one can say something, is this a good solution or not? Well, there are different perspectives one can put on this. You know, a solution is a good solution if it works, right? So that's the primary thing. So we want things to work, and then we want them to work as efficiently as possible. I mean, our task as engineers is to build something with the lowest possible cost that fulfill the requirements at hand. Okay, and cost here could be in actually money, or it could be cost in resources. energy, other types of resources. So these type of solutions where you divide and conquer are typically not optimal from a resource perspective or a performance perspective. Because if you can design the whole system, you can probably find a smarter solution than the solution you would get by dividing up the problem into small pieces and glue them together. Nevertheless, it could be like a joint approach, not splitting up the problem into sub-problems, so the overall solution is just way too complicated, way too hard to get it to work. And if it doesn't work, it's not a good solution. So at the end, this modularity that you divide it into smaller pieces, and then if you want to do a redesign, you can redesign the smaller pieces rather than redesign the whole thing, is often much more important than efficiency. Okay. So we sacrifice optimality and performance to get flexibility and modularity. Okay, so that's in general. So when it comes to communication networks, the overall problems are divided into layers. Okay, so we have a number of layers, and in each layer, which are stacked on top of each other, and the convention is that the lowest layer is called layer 1, and then layer 2, and so forth, and we then add up layers as we go up here. So what is a layer? A layer is something that provides a service to the layer above it by using the service of the layer below it. So this is, I realize that this is a little bit abstract right now, but layer 1 here can do something. It can provide, it can offer some type of service, and it offers services upwards. So it provides services up to layer 2, and layer 2 provides a service. So layer 1 provides a service to layer 2, layer 2 provides a service to layer 3, and so forth. And on top of everything here, we have some application software, which is using the service of the top layer here. Here we have a very nice service in the sense that we would like it to make it easy for applications to use the network, or basically to make it easy for people to program an application to use the network. While at the lower layer, we solve more fine-grained problems, for instance, moving bits over a fiber optical channel or something like this. But on the top here, we have more refined services. We will see this later on. Okay, so now layer 2 provides a service to layer 3. So how does layer 2 implement this service? Well, it implements that service by using the services provided by layer 1. So if we want to look at how services are used, the higher layers use the services of the lower layers. So just to say this once more, layer 1 provides a service to layer 2. Layer 2 provides a service to layer 3, and so forth. Layer 2, how does it implement the service it provides to layer 3? Well, it uses the service of layer 1. Okay. So was that somewhat clear? All right. Great. So and the idea here is that layer 3 does not use layer 1 services directly. It only uses layer 1 services indirectly through layer 2. So the interface between the layers is exactly this boundary between the layers. So there is no leapfrogging here, right? So layer 3 is not speaking to layer 1 directly. This is not allowed. Okay. Now, each layer then operates according to a protocol. And protocol is a set of rules for how two or more communicating entities in a layer at different nodes interact. Okay, so this is a very abstract sounding sentence, but it's actually a pretty good definition. And the objective of this lecture, for instance, is to clarify what that actually means. Okay, so if you don't understand it completely right now, go back and read this after the lecture, and hopefully this will become clear. Okay. Now, a set of layers with protocols is called a protocol stack. Okay, so therefore, there are some protocols which resides in layer 1, there are some protocols which resides in layer 2, and so forth, and a complete set of layers forms, together with the protocols, a protocol stack. Okay, questions? Yes?
Is the amount of layers connected to the stability?
Okay, so the question is the number of layers, if that's somehow related to stability.
Yeah.
Stability of what?
Of the program or the app?
Yeah, so no, not really. As we will see later on, the number of layers here is basically fixed by the type of model you use. So we will see later on in the models that we use regularly, the TCP/IP protocol stack, there is 5 layers, and there's always 5 layers. Yeah. Okay. But the type of services that you provide up here could be different. They could be of different quality, I would say, that would affect the performance of the application. Any other questions? No? Okay. So then let's make an example out of this to try to clarify a few things. So web browsing is a typical service that we use, I would say, on a daily basis, right? So what is the web? Well, the web consists of HTML documents and other resources which are located at services connected to the internet. So the web is basically a distributed database of information, I would say, in a way. So a web browser, like your favorite web browser, Chrome, Firefox, Safari, Internet Explorer, Edge, whatever you use, Opera, is then used to locate and display these documents. So the browser here is application software, an application that we use. The browser itself uses a services of a protocol stack in order to do its job. Okay. Now, to display these documents or videos or whatever we want to do, we use a uniform resource locator or URL. And it consists of 3 parts. It consists of a protocol field, explaining what type of protocol is used to handle this resource. A host, this is the name of the computer or server which actually physically has this information. And then a file path on that server. Okay. So the protocol here is HTTP, okay, which stands for Hypertext Transfer Protocol. And okay, so here we have the Chalmers website and the default path, the front page you get when you type this in. So when a user clicks on a link in a browser which is connected to this URL, what does the browser do? Well, it finds the IP address to this host, okay, and then connects to the host, and then requests the file, and then display the result. Okay, so these are the steps. So let's see how this works in essence. First of all, when the user clicks on a link called with the host name www.chalmers.sc, so the URL then connects the internet name, which is this, of the host. Now, this is very useful for us, right? Because we can sort of decode from this, okay, it's a web server, it's a Chalmers web server, and it's somehow located in Sweden. Okay, so it's useful for us, but it's useless for the computer to figure out where this host is actually is, right? For that, to connect to the server, the browser needs to know the internet address or the IP address of the host. Okay. It cannot ask the network directly, please connect me to this host, because the network doesn't understand what this means. The network only understands internet addresses. So we need to translate from the internet name to the internet address, and this is used by using a protocol. a protocol called Domain Name System Protocol, DNS. Okay, so to see how this works, we have a web browser running on a host. We have a DNS server, which is a host, another host, which runs basically lookup service that translates between internet names and internet addresses. And then we have the actual server that has the information that we are looking for. So the first thing that happens here is that the web browser issues a DNS query, DNS, Q for query, and it basically asks the DNS servers, please give me the IP address of this host. And then the DNS server answers. It issues a DNS answer section, and it says, okay, it's 129.16.71.21. That's your IP address. Okay. Okay. Now, you might have catched a little bit of a flaw here. What is that? Perhaps? I mean, how does the web browser know what the IP address is of the DNS server? Well, that's something that it's configured from the beginning. When the web browser or the laptop or computer here powers up, among the configuration it's getting is the IP address of the DNS server. Okay, second thing, connect to the server. So now the browser knows the IP address, which is good, but then it needs to open a connection to the server, and this is using a protocol called Transmission Control Protocol, or TCP. Applications, okay, so it can connect to this, somehow the web, this computer then can connect to this computer, but it also needs to specify what program on the server it needs to communicate with. And to do that, it uses port numbers. So the applications on a host is addressed by port numbers, because this host can be running many different types of server applications. Could run an FTP server, for instance, or a web server, or several other services. So connecting just to the host is not enough. We also need to tell the host, okay, what application on you would I like to communicate with? And that is using port numbers. Now, it is a fact that web browsers listens to port 80. Okay, so this is what's known as a well-known port. All web browsers or all web server softwares use the port 80. There are other ports one can use also, but this is the common one. Okay, and the web browser also use a port number because when data goes back from the server to the host which is running the web browser, the host also needs to know, okay, here I got some data from the network, to what application should I route this? Okay, and then one uses also port numbers here. So basically applications are addressed with port numbers. Hosts are addressed with IP addresses. Okay, so what happens now? Well, first of all, we open a TCP connection. Okay, and we do that by issuing a TCP connection request from an IP address, this IP address, to this IP address, which is this IP address. Okay, and then it also needs to specify from what software. Let me try it. From what software on the host would like to talk to what software on the server. Okay, now I circled the internet address here. Maybe I should do this. this is port 80, right? While this specifies the web browser. Okay? So now when we have issued this command, the web browser, or sorry, the host which is hosting the web browser, the host which is hosting the web server, sorry, then if everything is okay, it acknowledges and say it's okay. It could also say, no, it's not okay, I'm too busy, or whatever, right? But if everything works out, this is completes the second step. Okay. And now the third step is then to request the web page that we are looking for. Okay, so TCP IP. I mean, there's actually, now before we go to that, what I described here is a little bit simplified from the TCP, but this is essentially what's going on. Okay, but before going to the next step, are there any questions on this procedure? Right. Yes?
How does the DNS server knows all the IP address?
Okay, so how does the DNS server know all the IP addresses? Basically, it's like this, that hold that question. I will actually explain it a little bit later. But essentially, it's like this. When you build a website and you put it on a host, you buy a domain name, wchalmers.sc, and then you register that with a internet name register. And then when you put that on a computer, a server somewhere, as part of the process of actually putting the web server, firing it up, you issue a DNS record in the DNS system. So you tell, when you basically release the web server software, when you fire that up, you register your IP address with the DNS system. Yeah. Okay, any other questions? Okay, so what we have done now is that, first of all, we have translated www.chalmers.se to an IP address. With the IP address, we have established a connection using TCP between the host and the server. And also we have instructed the server that we would like to talk to port 80, which is the web server software. And we also said that whatever you send back should go to a web browser software, which has also address using a port number. Okay, so then the next step is to request a file. Okay, and to request the file, we use a protocol called HTTP. Again, as we said earlier, applications are addressed using port numbers. The web server software listens to port 80. The web browser uses a temporary port number, which changes from time to time. Okay, so what is the next step? Well, it's that the web browser talks to the web server using HTTP. Okay, so then it issues this command, get, okay, please give me this file, okay, using this protocol, and then it also tells what web server it would like to get this file from. Okay. Now the web server software gets this command and returns the file by first saying, okay, HTTP 1.1, okay, so this is the protocol I'm talking, 200 is the OK code, and then it gives us the information. And then the server web browser software basically displays this. Questions? Okay. So let's try to do this. The good thing about the internet is that we can actually easily do this as from a command prompt. So here I just fired up a terminal on my computer here. So if I want to find the IP address of Chalmers web server, I can use a command called dig. There are other commands, nslookup and so forth. And I say, okay, I ask DNS here, please give me the IP address for www.chalmers.se. Okay, and then I get an answer here. So what is on the answer here? It's a lot of information here, but basically the key information here is that it says www.chalmers.se has IP address 129.16.71.10. Okay, so now I've done this. So that's for step number 1. So let's connect to the web server. And then I use the TCP, and the easiest way to access this is through the telnet program. So I would like to talk to 129.16.71.10, and I would like to talk to port 80 on that computer. So by issuing the command now, what I did is I opened out a TCP connection to this computer with this IP address, and I told that computer I would like to talk to whatever software you have that listens to port 80. Okay, and now it's actually connected here. So the web server says, okay, I'm happy to talk to you. So now I have opened a connection to the web server software wherever it is, right? And now I can start to talk HTTP with this computer. So I write get. Okay, so what should I write now? I should write let me cheat here a little bit and look at my notes. Here we go. I should write this. Okay. /en/ page /default ASPX. Yeah. Okay. And HTTP/1.1. Okay, so basically here I told the web browser this is the file I'm looking for, okay, and this is the protocol that I speak. Okay, and then the next step to do is to specify, okay, on this host there might be several web pages running, so there could be not only Chalmers website could be running on this computer, it could be many different, right? So I need actually to specify which of the web servers I would like to talk to, and I would like to talk to the this one, and I would like to talk on port 80. Okay, and now I have issued the command. I told the web server software exactly which site I would like to do, and now I finish everything by entering a blank line. And if everything works well now, we should get the Chalmers web page. And we got a bad request. So what did I do wrong here? The requested host name is invalid. Okay, so here this just illustrates how tricky it is to get everything right here, because it should not be a space here, there should be a colon. Okay, so I'll have to do this again. Telnet. Okay, of course this doesn't work. Get /en/page/default host.aspx http/1.1. Okay, host www.chalmers.se:80. Okay, let's see. Let's see if this works now. Yes. No. Yes. It. No, it doesn't. Why doesn't it?
Should be a bit E in page. In your notes, you had pages.
Ah. Okay. I give it one more try, okay? Okay, so this is actually works now. So now this, it's a big page, right? It's a really big page. This is some type of image, I think. Okay. So the first thing I get from the web server is, yeah, I can serve you this, and I can tell you that the content is HTML. It comes in text. There is a character set. This is when it expires, blah, blah, blah. This is the server software, blah, 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 blah. And let's see, here, so the content length, these are the number of bytes that this file contains. So it's 95,849 bytes. Okay. And if then here comes the actual code, and this is then interpreted, HTML, which is interpreted by the web browser, then it displays everything. Okay. Questions? Okay. Then if we return to what we have done, we have now shown an interaction between many different protocols. We used HTTP, we used DNS, and we used TCP. Okay, and under the hood, we have used many other protocols that wasn't visible to us. So the question is, how are these related then to layers and services? So that's what we will explore now. On the very basic level, a protocol is then a set of rules that determine how two communicating entities, maybe the web browser software and the web server software, how they interact. It determines how messages are sent and received, and how they are interpreted, and commands and responses to these commands. So actions here So we have node A and we have node B. These could be hosts, or they could be routers, or some other things. But there are two different physical places here. And in a layer, say the nth layer, there is a protocol and another protocol. There are two different protocols here. We have protocol A and we have protocol B. We can have protocol C and so forth, right? There could be many protocols which resides in one particular layer. The main idea, however, is that the protocol A talks to protocol A on the other side. Protocol B talks with protocol B on the other side. I mean, there is no crosstalk between the protocols here. So protocol A, the piece of software hardware which is executing protocol A, is called the protocol A entity. Okay, you can think of this as a small piece of software, a process or something like that, which is running on this computer, this node. And it talks to another piece of software executing protocol A at node B. These protocols interact by sending messages back and forth to each other according to the language or the rules which are specified by the protocol. So if protocol A, for instance, happens to be HTTP, then these are HTTP commands that go back and forth. You know, requests and responses to these. Protocol B sends messages back and forth, and it talks between two different entities, both executing protocol B, and the messages here are then defined, the syntax or the terminology in these messages here and how to interpret that is determined by protocol B. So that could be DNS, for instance. Okay. Questions? Okay. So the purpose again of a protocol, what is that? It's to provide a service to the layer above it. Okay. So whatever this protocol does is it provides a service to the protocols which are above it. And to provide the service up in the stack, it uses services on the layer below it. See if we can make that a little bit more concrete. Let's start with the application layer protocols. And this is the highest layer in the protocol stack. Okay, so this is the layer which application software interacts with. Okay, so suppose we have some web browser software and we have some web server software. These are programs which are executed on two different nodes. Okay, the web browser software uses the services of the application layer, and it chiefly works with, for instance, with the HTTP protocol, which is executed here. The web server software is also using HTTP in its own computer. So these, the web browser talks to HTTP and the web server talks to HTTP. Okay. So HTTP and also DNS are application layer protocols, and that means, what does that mean? It means that HTTP and DNS provide communication services, to application programs, web browsers, email clients, and so forth. HTTP and DNS use the transport layer services to provide the services to the application programs. So now, how does this work? There is some request coming from the web browser software down to HTTP, which sends a message over to its HTTP entity on this side, which then feeds it up to the web server. The web server responds to this and sends a message back to this. Okay. Now, this is the logical flow of information. It goes horizontally here. But in the physical flow of information actually goes down the protocol stack until it hits the physical layer when actually data is transmitted between nodes. So HTTP, to do its job, it uses TCP to actually send the messages. Okay? HTTP needs to send HTTP messages to its corresponding process on the other side, but it's actually done by using TCP services. Okay, so the actual data flow goes down the stack, and then it goes over to the other side, and then goes up the stack on the other side, like this. So the purple line here is where the physical data flow goes, and the dashed line here are the logical flows. Okay. Now, of course, TCP, we see that this is a dashed line, so this is actually a logical connection. So TCP in itself is using the service of the layer below it. And there are a couple of layers here which I haven't put up on the slides. We will see them later on. Right? Okay. So from this slide, I would like you to get the following key messages. A protocol, HTTP, resides in a particular layer. In this, for HTTP, it's in application layer. It talks to the other HTTP process, which is running at the application layer at some other node. And logically, these sends information back and forth like this. Physically, these messages goes actually by using the services of the layer below, which takes care of transmitting this information. Now, how does TCP transmits its messages? Well, it's actually using the network layer which is below it, which is using the layer below it, and so forth. Right? We will see that in more detail later on. Right? But again, application layer provides a service to the application program, and it uses the services of the transport layer. The transport layer is providing services to the application layer, and it uses the services of the layer below it. Is this reasonably clear? Questions? No? Okay. So then a small quiz then. So if we take the first question here, what is true? 1, a layer can contain many protocols. A protocol can span many layers. There is exactly one protocol in each layer. I'll give you a few seconds to think about this. Okay, so how many for 1? How many for 2? And how many for 3? Yeah, so it's a little bit of a split here. Okay, so actually the correct answer is a layer can contain many protocols. Okay, this is wrong because a protocol can only be in one layer. Okay, so HTTP resides in the application layer. It has no part of the transport layer. Okay. And there are many protocols which could be in the application layer. We just saw that HTTP and DNS both belongs to the application layer. And there is a bunch of other protocols there. Okay. But the most important thing is that the layer, a protocol resides in exactly one layer, and a layer can contain many protocols. So if we have a layer here, we can have DNS, HTTP, etc., right? But the layer below it cannot have any components which are related to a protocol above it or below it. Okay. Second thing, what is true by an application program, for instance, a web browser? 1, it's a protocol in the application layer. 2, it uses the services of the application layer. 3, it provides services to the application layer. So I'll let you have 10 seconds for this also. Okay, so how many for 1? 2? And 3. All right. Very good. So it's something the software, software relies on top of the application layer, and it uses the services of the application layer. So this is correct. Application software is not the protocol, and it does not provide any services down the stack, right? services are provided upwards in the stack, and services are used down the stack. Okay, number 3 here. So what is the main purpose of a protocol? 1, to provide services to the layer below it, to interact with the corresponding layer at some other computer, or to provide services to the layer above it. So how many for 1? 2? And 3. Yeah. So the thing here is that actually this is both 2 and 3 are somewhat correct, or both of them are correct statements, but the main purpose is to provide services, right? And it happens to do that by interacting with other ones at some other computer. So when you have the quiz on Monday at the exercise, you can see that so many statements could be correct, but there is one statement which is more correct than the others. It's almost like taking your driver's license again, right? It's same principle here. Okay, good. So let's continue. So to summarize, a layer is a set of related communication functions that provides a service to the layer above it using the service of the layer below it. Right? I think I hammered this point down a couple of times. I hope it's becoming clear now. So this is all fine, but how do we define and group related communication functions into layers? So basically, how do we define what the purpose, what is the function of that layer? Right? Because we could do this in many different ways, and how do we specify these services? How do we define what the service does and does not? What are the attributes and qualities and performance of that? Okay, some guidance to this is supplied in form of reference models. Okay. First of all, the word model, what does that really mean? Well, you work with models every day. A model is a simplified description of reality. Okay? So what I'm trying to say now is that the reference models that we talk about somewhat tells you what the protocols are in reality. Real implementations, real protocol stacks and so forth are a little bit more complicated and sometimes violates the rules that I already told you today, right? But anyways, to be able to understand how the practical real implementation works, we need to use models in order to explain and understand them. And once we understand them, we can understand how real protocols are violating these rules in smaller respects, right? Okay. So there are two main models here, and one is called the Open System Interconnection or OSI model. It has 7 layers, very, very influential in how things are modeled and explained, but it's rarely used in practice. I don't think it's used at all, actually, to be honest. And then there is the Internet Reference Model or TCP/IP model. It has 5 layers, or is it 4 layers? Well, if you Google this, you will get different results. Okay, so it's either 5 or 4, depending on how you think about it. So it's an empirical model in the sense that it was designed before the OSI interconnect model and before one started to think very strictly about protocols, layers, services, and so forth. So it's basically evolved through a research project and then over the years become the dominant model that's used on the internet today. And it's heavily used in practice. Okay. So we have, what should we say, the theoretical clean model here, well thought out and precise in many details. And here we have the practical ugly model, but it's what's used. Okay. So the focus of the course will be to talk a little bit about the theoretical concepts here and see how that maps onto reality. And actually we would simplify reality a little bit, because if we go into the nitty-gritty details, we lose the overall idea about what the protocols are. Basically, we won't see the forest for all the trees, right? So what I would tell you now would be an approximation of the truth, the true protocols. But I'll cut out some details which are just confusing in my mind. But if you want to know the nitty-gritty details, by all means, Google is your friend, right? And then you can figure out everything if you like. Okay, but let's take a break, 15 minutes maybe.